Hello all. Today we are going to see about Markov decision process. This is an introduction to reinforcement lecture and this is the first reinforcement lecture. We'll see what is Markov decision process. Markov decision process, that is MDP, is a mathematical framework to describe an environment in reinforcement learning. So I understand at this point of time this might look hazy because we first need to understand what is environment and what is reinforcement learning. So we'll understand that first, maybe later you'll gain a clarity as and when we move ahead. Okay, so here there are two pictures, this one and this one. So this is a formal picture and this is an informal picture. So here we'll first look at the informal picture to understand what is reinforcement learning. So here in this informal picture, there's an agent, this is a dog, and the environment here is a girl who is having a stick in her hand. So the agent can be thought of as a robot which is playing chess in real-time scenario I'm speaking about. So the chessboard is the environment in real-time scenario and the agent is a robot. So here in an informal example, what we are seeing here is a dog. Okay, so the dog will show some actions to the environment and in turn the environment is going to show some rewards back depending upon the action shown. For instance, if the dog is jumping with joy on the girl, so then the girl will show some positive actions. So that is a positive reward, and the dog will understand that. In case if the dog is jumping on anger on her and it is biting her, then she will show some negative rewards, negative reactions. So then the agent is supposed to align its action depending upon the rewards it is getting. So if it's a good dog, then it will align its actions, right actions in such a way that it is getting the positive rewards. That's what's the goal of the real-time reinforcement learning agent. So the agent will align its actions depending upon the rewards given by the environment, and through that it is going to achieve the goal it is for what it is destined for. Now we may understand what is reinforcement learning definition. Reinforcement learning is a learning technique by which the learner learns to behave in an interactive environment. So the environment is going to keep on interacting with the agent by the with respect to the action it is showing to the environment. So through the rewards it is going to give back. So the learner often is called as the agent, which discovers the actions by getting the maximum reward. So the agent is supposed to get the maximum rewards from the agent, so through which it is going to align its action and achieve its goal. So that's the crux of reinforcement learning. Now we will understand this formal diagram. So here in this formal diagram, so we see an agent, so which was a dog earlier, and the environment which was the girl earlier. So this environment can be anything, as a chessboard, or if the agent is trained for picking an object, then the place where the object is placed is going to be the environment. So we see an ST, that is state, and we see a reward RT, and we see ST plus 1 is, that is another state, and the RT plus 1 it's another reward. So we'll understand this. So when the agent is actually interacting with the environment, so the agent can be in n number of states. For instance, if the dog is lying on the floor, that is one state. If the dog is standing up, then that is another state. For each and every state in which the agent is in, it will exhibit certain action A. So with that action A, the environment is going to give some reward. And with the reward it gets, it is going to either stay in that particular state and keep exhibiting that action, or it will transit to another state, ST plus 1, and it will choose some other action which is from that particular state. So this is going to go again and again till the goal is reached. That's how reinforcement learning should be understood as. Still, we may not be able to understand the Markov decision process. That's fine. So we'll gain clarity as and when we move on. We'll have a closer look of about the components of reinforcement learning. So the first component is the environment. We already saw the girl who was having the stick in her hand. So any outside world, so which is in which the agent is interacting to achieve a particular goal, that is the environment. And the state. So while interacting with the environment, so in the process of achieving the goal, so for instance, playing the chess against a human or picking up a job, the agent can move from one state to another. It can show itself in exhibit itself in many other states. For instance, a robot sitting in a chair is one state, standing up another state. So it is in the process of achieving its goal. So while doing this, while getting involved in this process, it can be in a number of states. So primarily, the current situation the agent is in. So at present, it is in. So that is called as a state. The action at each and every state S. So it might choose any action. So for instance, it can go up, it can go right, it can go down, it can go left. So there are n number of actions that it can opt to choose. It can opt at a particular state. So that is an action, the choice of agent it makes at particular time step. That is the action. The reward is primarily the numerical value that is got from the environment. So for each and every right action and the state transition it takes, it is going to get a positive reward. So the goal is that it has to get the maximum number of rewards. Through that it is aligning its right number of actions, and through that it is achieving the goal for which it is destined for. So that's the idea. Policy. Policy is nothing but it's a function, so that is used to map the agent state to action. Though it is in this particular state S and it can move to another state ST plus 1. So while moving, so it can choose either of these actions to this state. So the policy is nothing but while taking a transition from one state to another, what is the action it is taking. So it is not only constrained with these two states, the agent might transit to n number of state till it reaches the goal. So for at each and every state, what is the right action it is taking so that it is maximizing the rewards while in the process of achieving the goal. So that is the policy. So what we are interested in finding is that at each and every state, what is the right action it is supposed to be taken. So what is a set of actions that is to be taken at each state. So that is called as a policy. Okay, so the value is nothing but the future reward. So value is given to the state. Okay, so the value is the function that is, the value is given to each and every state. So each and every state is going to get a value so that when an agent is transiting from one state to another, for instance, this is a state is having some value. The agent will only decide to shift to the state depending upon what is the predicted return it would get if it transits from this state to this state. So that is called as the value. Okay, so these are the components of reinforcement learning. Okay, so the reinforcement learning is also a type of machine learning technique. So we should understand that how does it differ from the rest of the machine learning techniques. A supervised learning, so is also one of the machine learning techniques in which we have labeled training data set. So we have labels. For instance, for example, when we are building a classifier which is supposed to classify the dog pictures and the cat pictures. Okay, so when a dog is shown, dog picture is shown, it should classify that as a dog. When a cat picture is shown, it should classify it as a cat. Let's say we are building such a supervised learning model, then we would have already got the training data set which is labeled. So that means the cat pictures are all tagged as cat and dog pictures are all tagged as dog. So with these tags and the dog pictures and the cat pictures, it is associating with the labels and the features of the dog and cat pictures, and it is coming to a conclusion and it is building a model so that whenever a cat picture is shown, so without a tag, that it is without the label, then it will automatically classify that it is a cat, and respectively the same for the dog picture. That is supervised learning. So with the labels and associating that with the features of the data, that is the pictures, the pixels. The pixels are going to be the features. Then that is supervised learning. The unsupervised learning on the other side will not have, the training data will not have the labels. The dog pictures will not be having the label, but still it will do some grouping. So that we call it as clustering. So it is as simple as, like, for instance, we have apples and oranges. A baby tries to cluster it based upon the color of the fruit and the shape of the fruit. So without knowing the labels, we are grouping based upon the similarity of the features of the data. So that is unsupervised learning. The reinforcement learning, on the other side, it is reaching its goal depending upon the positive and the negative rewards it is getting from the environment, and it is aligning its sequence of actions. It takes and while shifting from one state to another. So that is reinforcement learning, and that's how it differs from the rest of the machine learning techniques as well. Okay, so now our goal was to understand Markov decision process. So before even we understand Markov decision process, we need to understand what is Markov property. So Markov property is all about, like, state transition probabilities, understanding state transition probability, a state S, ST. So here it is ST. So a state ST is Markov if and only if, given we are in state ST, the probability of the transition. So when the state transition is taken from ST to ST plus 1. So this the probability of going to this state is only dependent on the probability of this particular state ST and not on the earlier states. So we could before shifting to ST plus 1 from ST, there could have been n number of states. So T minus 1, ST minus 2, and so on. But we are not bothered about the probabilities of the earlier states. We are only bothered about the probability of the current state, the immediately previous state. So to predict the probability of the next state. We'll take an example to understand this better. So let us assume that the robot is seated on a chair. Okay, that is one state. It stood up, that is another state, and it is picking up an object, that is another state. So the current state is to be understood as the picking up the object. It is having some object in his hand, that is the current state. The prediction of the robot taking the other state, okay, so that is dependent only on the probability of this particular current state and not on the probabilities of these states, the earlier states. That is about the Markov property. So this should be understood first. Okay, so we have not still understood Markov decision process. So before that, we will understand what is a Markov process or a Markov chain. Okay, so you see a state transition diagram here. So this is what a Markov process. So these are the states. The circle ones are the states. Even this is a state. This is the final state. Okay, so these are the states. And why we call this as Markov chain is that we are going to repeat the process from one state to another. So again and again. So we can be in sitting state and we can transit to standing state and we can move from there and then we can come back to the sitting state from the standing state. So this is going to go again and again and again. But there are numbers associated, you see that. So this is a probability. So for instance, we'll focus this particular state. Let's say the robot is in the sitting state. So the probability of the robot transiting from sitting state to standing state is 0.6. That's what it's shown here. And the probability of the robot shifting from sitting states to the shutdown state, the final state, is 0.1. It's very less. And the probability that a robot can raise its hand from the sitting state is 0.3. So these are the probabilities of the state transitions from this particular state. So if you look closer, when you add up all these probabilities that is emerging out of the state, that 0.1 plus 0.6 and 0.3, they add up to 1. Because we are dealing with probability, it has to add up to 1. So this is the state transition probability. What is the probability that a particular state will get transited to another state? So that's what Markov process is. And we have to remember the Markov property that we saw earlier. So the probability that the robot will transit from sitting to standing is only dependent upon the probability of this particular state and not on the earlier state in which the robot was. Okay, so now we haven't seen Markov decision process yet. We have only seen the Markov process. This is an exact difference between the Markov process and the Markov decision process. You see an additional A here in Markov decision process. So Markov process only tells us what is the probability that robot will shift from one state to another. But in Markov decision process, what we do is that we associate an action. So from each and every state, there might be n number of actions that we can take while we transit from one state to another. So we are also interested in monitoring this action along with the state transition probabilities. That is what Markov decision process is about. Okay, so the rewards, this is a reward process. This is a four tuple. The Markov reward process is defined by the set of states, the state transition probability P, and the rewards that we get, and the discounted factor. So the discount factor we'll understand better, we'll gain more clarity as and when we work out examples. But at this point of time, how this should be understood is that the discount factor is nothing but like how, what is the importance that you give for the future rewards, that is the expected rewards. We do not know, right? Like when we are in one state, we might move to another state, but we do not know what is the reward that we get when we move to the other states. So we have some weighted we give some weights to that. So that is discount. So at this point of time, this could be understood this way. We'll gain a lot of clarity as and when we work out with examples. The state transition, the same state transition diagram that we saw earlier is associated with the reward. That is where this Markov decision process is gaining importance. So like along with the probability, state transition probability, we have also a reward. So that's what it says. So from while transiting from one state to S to S prime, so we get a reward also. So why we have it as t plus 1 is that, so this particular reward R is equal to minus 1 is that, so that an agent gets when it leaves from this state to any other state. So that's why it happens this, and it is said to the agent receives this award when it leaves the state. So that's why it is taking at the time step t plus 1. So that's why we have put it this way. So the probability that the reward function is as simple as this. When it transits from one state to another state, what is the reward it is supposed to get? So that's what we are interested in. And our initial goal that we should remember, the agent is supposed to transit from one state to another state and consequent states to maximize the rewards. That's how it is aligning the action. That's why we are interested in finding what is the reward that we would get when we transit from one state to another. So that's where the Markov process and the Markov decision process makes a difference. Now we can understand an MDP. So MDP is a set of states and set of actions we take at each and every state, and the probability associated with it, the rewards, and the discount factor. So this is what is a MDP. So we can understand this. What is the probability that the robot transits from one state ST to ST plus 1, that is S prime, by taking a particular action. So why? Because at each and every state we can have n number of action. So let's say we have go up, go down, or go right and go left. So these are 4 set of action. What is this small a? So what is the particular action? Go right or go left. So that is taken from the set of these 4 actions. So that is also associated in predicting the next state transition probability. So that's how it should be understood as. And the reward is the numerical value that we get when we do the state transition by choosing a particular action. Sorry. So the policy pi. So there's one more terminology, policy pi. So the policy pi defines the thought behind making a decision. It defines the behavior of an RL agent. So it's basically at each and every state we are taking an action, right? So when we keep on transiting from one state to another, from each and every state we are going to pick up an action, right? So what are the set of actions we are taking? What are the right set of actions we are taking at each and every state? That string of actions we call it as pi. So the pi can be thought of as a probability distribution over the actions given the states. Okay, so it's a probability distribution from this particular state. What is the probability that you choose a particular action? What is the probability that you take right? What is the probability that you take left? What is the probability you go up or go down? So that is policy pi. So and it is also can be thought of as a set of actions we are bothered about, like choosing the right set of actions that should be chosen for each and every state when we transit from one state to another depending upon the reward. So there are three things that should be understood. We are taking a state transition from one state to another, and we are doing so, we are keeping in mind of the rewards that we are collecting, and also we are also taking into account the actions. So what is the right action that would maximize the reward? So actions, reward, and the state transition. So three things that should be kept in mind. Yes, one more function we have, utility function. So the reward function is only bothered about like what is the reward that we get when we transit from one state to another. So but we are interested in the overall, our vision is to reach from the starting state to the final goal, right? So when we are doing so, we will have n number of state transitions in between, and when we will have the rewards, and we will choose each and every action. So what utility function is bothered about is that you see a pie here, right? So we are bothered about the policy. The policy is all about choosing the actions. So the utility function is for a particular policy. There can be a number of policy, but for a particular policy, what is that? So we are in state yes, right? And we are, what is the probability that we will go to these set of states for using this policy pi? So policy pi is nothing but the set of actions we take. For instance, we are in state, starting state, we will move right, then we will take a right, go up, down. So this is a policy pi. So and then we reach the goal. So this is one policy, pi 1. So there can be a number of policies. So for this particular policy, what is the expected probability of transiting from these states to another, multiplied by the sum of the discounts. So this is the weight factor we were talking about. So this is a prediction. So what is the reward that you would get when you land in the consequent states? That's what we are bothered in. So this is indirectly, this equation is telling us that we are supposed to maximize the rewards whenever we take a transition from one state to another. So that's the goal. So that's the utility function, because there can be a number of policy. There can be a number of sequence of actions that you might take while you take a state transition. But you might also have to monitor the rewards you get while you take a state transition. That is the pi of s. So the pi of s, that is, I'm sorry, that was utility function u of s, and the pi of s is nothing but the policy. The policy we are interested in. So that is the maximum. There are a of s is the set of actions that you take from each and every state, and what is the right action you take. So at each and every state we have this utility function and the probability of state transition. But which action gave you the maximum utility value? So that's what this equation is telling us. So whether the go right action is giving you the maximum value, or the go left action is giving you the maximum value, or go up or go down. So which was giving the maximum value. So that's how we align the set of actions we take at each and every point of time. So the utility function in general. So this is a Bellman equation actually. So utility function of a particular state is nothing but the reward that you get at that particular state plus the discount factor multiplied by the maximum probability. So you take what is the policy that you gave the maximum utility value. So this is a prediction. This is S prime is got from the future states. That's how we'll understand. We'll understand all this when we work out an example in the upcoming videos, but as of now it can be thought of this. So while we take a transition from one state to another, what is the right action we are supposed to make? That's what utility function and the policy pi is telling us. Okay, so this is an example policy that we see. So you see here, this is one goal state and another goal state. So a good agent is supposed to reach this goal 10, right? Because that is having the maximum reward. So we are not supposed to stuck here. So these are the policies you see. So let's say the agent is here. So then if agent can land in any state, right? So it's random. So let's say we are in this state. Then this state says that the policy is right. So we are supposed to move this way. So this state also says that it move right. This state also says that we should move right. And this state says we should stay. Because we have achieved the maximum goal, we can settle here. Let's say if you're landed, if we have landed here, then it says that, okay, this is not the right place, you're supposed to go down. And from here, we will move right. This is a good policy. So this is the best policy the agent has learned on its own. But if you see here, this is a bad policy. Maybe the agent has learned this bad policy in the initial state, and as and when the training, the time moves on, it will learn the best policy. See here, if you can see here, if the agent is here, it says that it should move left. And this says that it should stay. It's not supposed to stay, right? Because the maximum goal is lying here. So it should have been right here. So we should have, instead of stay, the action should have been right. So then only we can move it here. So move towards this state. And this should have been right instead of left. Then only we can move. So we can align our actions. So this policy is a bad policy. Maybe this was an initial policy learned by the agent. But the reinforcement learning is all about like learning the right policy over the period of time. Yeah, how do we know that we learned the best policy? How do we learn the best policy? There are techniques to do that. Value iteration and policy iteration. So we will we'll see through worked out examples in the upcoming videos. But in this lecture, what we have seen is that we have seen what is in Markov decision process and how is that going to help the reinforcement learning technique to find the best policy. So that is achieved, so that the goal is achieved by getting the maximized rewards. We have done the preliminaries, and in the upcoming videos we will see through the examples how do we find the best policies. These are the references from which this video has been taken, and thank you.